4.3 Amplitude Modulation Am. In the last section, we began our discussion of amplitude modulation by introducing the DSB-SC amplitude modulation because it is easy to understand and to analyze in both the time 1.5.2 amplitude modulations and DEMODULATIONS and frequency domains. However, analytical simplicity does not always equate to simplicity. In practical implementation, the coherent demodulation of a DSB-SC signal requires the receiver to possess a carrier signal that is synchronized with the incoming carrier. This requirement is not easy to achieve in practice, because the modulated signal may have traveled hundreds of miles and could even suffer from some unknown frequency shift, the bandpass. Received signal in fact has the form of RT equals ACMT 2 cos L WC plus WT 2 equals AMT 2 cos I W plus W T0 DL, in which W represents the Doppler effect while comes from the unknown delay 2. To utilize the coherent demodulator, the receiver must be sophisticated enough to generate a local oscillator cos W plus W T 0 D purely from the received signal RT. Such a receiver would be harder to implement and could be quite costly. This cost is particularly to be avoided in broadcasting systems, which have many receivers for every transmitter. The alternative to a coherent demodulator is for the transmitter to send a carrier a cos wet along with the modulated signal Mt cos wet, so that there is no need to generate a carrier at the receiver. In this case, the transmitter needs to transmit at a much higher power level, which increases its cost as a trade-off. In point-to-point communications, where there is one transmitter for every receiver, substantial complexity in the receiver system can be justified, provided its cost is offset by a less expensive transmitter. On the other hand, for a broadcast system with a huge number of receivers for each transmitter, it is more economical to have one expensive high-power transmitter and simpler, less expensive receivers because any cost saving at the receiver is multiplied by the number of receiver units. For this reason, broadcasting systems tend to favor the trade-off by migrating cost from the many receivers to the fewer transmitters. The second option of transmitting a carrier along with the modulated signal is the obvious choice in broadcasting because of its desirable trade-offs. This leads to the so-called AM amplitude modulation, in which the transmitted signal less than π is given by FAMU equals a cos wet plus MT cos wet equals A plus MT cos wet 4.8 A 4.8 B. The spectrum of FAMT is basically the same as that of FDSBSDT equals MT cos wet except for the two additional impulses at plus or minus JC. 1A Ham T2 MF plus JC plus MF F plus 2 8 F plus JC plus 8 F JC 4.8 C. Upon comparing FAMT with FDSBSC chord equals MT cos wet, it is clear that the AM signal is identical to the DSBSC signal with A plus MT as the modulating signal instead of MT. The value ofA is always chosen to be positive. Therefore, to sketch less than π, we sketch the envelope IA plus MTI and its mirror image IA plus MTI and fill in between with the sinusoid of the carrier. Frequency JC, the size of A affects the time domain envelope of the modulated signal. Two cases are considered in Fig. 4.8. In the first case, A is large enough that A plus MT 0 is always non-negative. In the second case, A is not large enough to satisfy this condition. In the first case, the envelope has the same shape as MT, although riding on a order of magnitude. A. In the second case, the envelope shape differs from the shape of MT, because the negative figure 4.8 AM signal and its envelope A plus MT greater than O for all 1. (4.3 Amplitude Modulation AM 153) A plus MT greater than 0 for all I. B. One T equals 1. I D. Envelope A plus MT I I E envelope IA plus MTI part over plus MT is rectified. This means we can detect the desired signal MT by detecting the envelope in the first case when A plus MT greater than 0. Such detection is not possible in the second case. We shall see that envelope detection is an extremely simple and inexpensive operation, which does not require generation of a local carrier for the demodulation. But as seen earlier, the AM envelope has the information about MT only if the AM signal A plus MT coswet satisfies the condition A plus MT greater than 0 for all T. Let us now be more precise about the definition of envelope. Consider a signal ET coswet. If ET varies slowly in comparison with the sinusoidal carrier coswet, then the envelope of ET coswet is i.e. Ti. This means CEQ 4.8b that if and only if A plus MT 0 for all T, the envelope of less than OAMT is IA plus MT I equals A plus MT.
In other words, for envelope detection to properly detect M, T, two conditions must be met.
A. Phi bandwidth of MT. B. A plus MT 0. This conclusion is readily verified from Fig. 4.8d and E. In Fig. 4.8d, where A plus MT 0 A plus MT is indeed the envelope, and MT can be recovered from this envelope. In Fig. 4.8e, where A plus MT is not always positive, the envelope IA plus MT I is rectified from A plus MT. And MT cannot be recovered from the envelope. Consequently, demodulation of Am T in Fig. 4.8d amounts to simple envelope detection. Thus, the condition for envelope detection 1, 5.4 amplitude modulations and DEMODULATIONS of an AM signal is A plus MT 0 for all T 4.9a. If MT 0 for all T, then A equals 0 already satisfies condition 4.9a. In this case there is no need to add any carrier because the envelope of the DSBSC signal MT cos I court is MT, and such a DSBSC signal can be detected by envelope detection. In the following discussion we assume that MTF 0 for all t, that is, MT, can be negative over some range of t. Message signals MT, with 0 offset, let plus or minus MP be the maximum and the minimum. Values of MT, respectively, see Fig. 4.8. This means that MT, MP, hence, the condition of envelope detection 4.9a is equivalent to 4.9b. Thus, the minimum carrier amplitude required for the viability of envelope detection is MP. This is quite clear from Fig. 4.8. We define the modulation index micro as MP micro equals A 4 10A. For envelope detection to be distortionless, the condition is A MP. Hence, it follows that 4 10B is the required condition for the distortionless demodulation of AM by an envelope detector. When A less than MP, EQ 4 10A shows that micro greater than 1 overmodulation. In this case, the option of envelope detection is no longer viable. We then need to use synchronous demodulation. Note that synchronous demodulation can be used for any value of micro, since the demodulator will recover signal A plus MT. Only an additional D block is needed to remove the DC voltage A. The envelope detector, which is considerably simpler and less expensive than the synchronous detector, can be used only for micro S1. Message signals MT, with non-zero offset, on rare occasions, the message signal MT will have a non-zero offset such that its maximum M max and its minimum MM IN are not symmetric, that is. In this case, it can be recognized that any offset to the envelope does not change the shape of the envelope detector output. In fact, one should note that constant offset does not carry any fresh information. In this case, envelope detection would still remain distortionless if, with a modified modulation index definition of M max ln min micro equals 2a plus ln max plus ln min 4 1 la 4 llb. Example 4.4 Sketch Jam T for modulation indices of micro equals 0.5 and micro equals I when mt equals b cos j 111 t. This case is referred to as tone modulation because the modulating signal is a pure sinusoid, or tone, figure 4.9. Tone modulated AM. A micro equals 0.5. B micro equals 1. 4. 3 Amplitude Modulation AM 155. In this case, M max equals B and MMIN. 4.10a is B. Hence the modulation index according to EQ. Hence, B equals micro A and therefore B micro equals 2a plus B plus B. B A MT equals B cos W MT equals micro A cos W MT. PAM T equals A plus MT. Cos WT equals A L plus micro cos WMT cos wet. Figure 4.9 shows the modulated signals corresponding to micro equals 0.5 and micro equals 1, respectively. A micro equals 0.5. 1 plus 0.5 cos W 111 t. IA 2A2 1 A sideband and carrier power. Single quote backslash micro equals I 1 plus cos W nt single quote B backslash backslash I A 1. The advantage of envelope detection in AM comes at a price. In AM, the carrier term does not carry any information, and hence, the carrier power is wasteful from this point of view. Am T equals a cos Vt plus M T cos Vt. Single quote dash comma dash dash single quote dash dash dot dash single quote. Carrier sidebands. The carrier power Pc is the mean square value of a cos Vt, which is a 2/2. The sideband power Ps is the power of Mt cos Vt, which is 0.5 square meters T (CEQ). 3.93. Hence, A2 PC equals 2 and the useful message information resides in the sideband power, whereas the carrier power is the used for convenience in modulation and demodulation. The total power is the sum of the carrier wasted power and the sideband useful power. Hence, Rj, the power efficiency, is useful power Ps Rj total power Pc plus Ps. For the special case of tone modulation, Mt equals micro cos Wmt and M2T dash dash 100%. A2 plus M2T A2 M2T equals underscore micro underscore 2156 amplitude modulations and DEMODULATIONS. Hence, micro 2 Rj equals 2 plus micro 2 100%. With the condition that 0 micro 1. It can be seen that Rj increases monotonically with micro, and F max occurs at micro equals I, for which F max equals 33%. Thus, for tone modulation, under the best conditions, micro equals 1, only 1/3 of the transmitted power is used for carrying messages. For practical signals, the efficiency is even worse on the order of 25% or lower compared with the DSBSC case. The best condition implies micro equals 1. Smaller values of micro degrade efficiency further. For this reason, volume compression and peak limiting are commonly used in AM to ensure that full modulation micro equals 1 is maintained most of the time. XRMPLE 4.5 determine Rj and the percentage of the total power carried by the sidebands of the AM wave. For tone modulation when micro equals 0.5 and when micro equals 0.3. For micro equals 0.5. Micro 2 0.52. Rj equals 2 plus micro 2.100% equals 2 plus 0.5 2.100% equals 11%. Hence, only about 11% of the total power is in the sidebands. For micro equals 0.3. 0.32. Rj equals 2 plus 0.32100% equals 4.3%. Hence, only 4.3% of the total power is in the sidebands that contain the message signal. Generation of AM signals. In principle, the generation of AM signals is identical to that of the DSBSC modulations. Discussed in Sec. 4.2 except that an additional carrier component a COSWET needs to be added to the DSBSC signal. Demodulation of AM signals. Like DSBSC signals, the AM signal can be demodulated coherently by a locally generated carrier. Coherent, or synchronous, demodulation of AM, however, defeats the purpose of AM, because it does not take advantage of the additional carrier component a COSWET. As we have seen earlier, in the case of micro 1, the envelope of the AM signal follows the message signal. MT. Hence, we shall consider here two non-coherent methods of AM demodulation under the condition of 0 less than micro 1, rectifier detection and envelope detection. Rectifier detector. If an AM signal is applied to a diode and a resistor circuit Fig. 4. 1.0. The negative part of theme wave will be removed. The output across the resistor is a half-wave rectified version of the AM signal. Visually, the diode acts like a pair of scissors by cutting off any negative half-cycle of the modulated sinusoid. In essence, at the rectifier output, the AM figure 4. 10. Rectifier Detector. For AM. Single quote dash. A plus MT cos WCF. Single quote. Single quote dot comma dot. Single quote. Single quote. 4.3 Amplitude Modulation AM 157. VRT A plus MT. T1. A plus MT. 1. A plus MT. 7R. A plus MT cos wet. Low pass. Filter. Signal is multiplied by Wt. Hence, the half-wave rectified output VRT is VRT equals A plus MT cos wet WT 4.12 equals A plus MT cos wet plus cos wet ICOS 3 wet plus ecos sweat 4.13 equals A plus MT plus other terms of higher frequencies. Closing square bracket, opening square bracket. 4.14. When VRT is applied to a low-pass filter of cutoff BHZ, the output is A plus MTN, and all the other terms in VR of frequencies higher than BHZ are suppressed. The D term AN may be blocked by a capacitor, Fig. (4.10) to give the desired output MTN. The output can be doubled by using a full-wave rectifier. It is interesting to note that because of the multiplication with WT, rectifier detection is in effect synchronous detection performed without using a local carrier. The high carrier content in AM ensures that its zero crossings are periodic and the information about the frequency and phase of the carrier at the transmitter is built into the AM signal itself. Envelope detector. The output of an envelope detector follows the envelope of the modulated signal. The simple circuit shown in Fig. 4. LLA functions as an envelope detector. On the positive cycle of the input signal, the input grows and may exceed the charged voltage. On the capacity VCT, turning on the diode and allowing the capacitor C to charge up to the peak voltage of the input signal cycle. As the input signal falls below this peak value, it falls quickly below the capacitor voltage, which is very nearly the peak voltage, thus causing the diode to open. The capacitor now discharges through the resistor R at a slow rate, with a time constant RC. During the next positive cycle, the same drama repeats. As the input signal rises above the capacitor voltage, the diode conducts again. The capacitor again charges to the peak value of this new cycle. The capacitor discharges slowly during the cutoff period. During each positive cycle, the capacitor charges up to the peak voltage of the input signal. And then decays slowly until the next positive cycle is shown in Fig. 4.11b. The output voltage VCT, thus, closely follows the rising envelope of the input AM signal. Equally important, the slow capacity discharge via the resistor R allows the capacity voltage to follow a declining 1.5/8 amplitude modulations and DEMODULATIONS. Figure 4. 1.1. Envelope detector for AM signal, comma single quote V RC too large C A B plus envelope detector output envelope comma dot backslash comma dot 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 comma envelope capacitor discharge between positive peaks causes a ripple signal of frequency V. In the output, this ripple can be reduced by choosing a larger time constant RC so that the capacitor discharges very little between the positive peaks RC1, WC. Picking RC2 large, however, would make it impossible for the capacitor voltage to follow a fast declining envelope. See Fig. 4. L pound. Because the maximum rate of AM envelope decline is dominated by the bandwidth B of the message signal MT, the design criterion of RC should be 1 we RC less than I 2T B or 2T B less than -1 we RC. The envelope detector output is VCT equals A plus MT with a ripple of frequency we. The D term A can be blocked out by a capacitor or a simple RC high-pass filter. The ripple may be reduced further by another low-pass RC filter.